Hi everyone. Today we will be learning about two important topics, Lewis dot structures and molecular geometry. What are Lewis structures?
Lewis structures are diagrams that show the location of valence electrons and bonds in atoms, covalently bonded molecules, and ions. Let's start by drawing Lewis structures for single atoms. First, count the number of valence electrons in the atom. Nitrogen, for example, has 5 valence electrons. Next, place the electrons counterclockwise, one by one, around the atom until you run out of electrons. There should be a maximum of 8 electrons for individual atoms. Let's practice. Draw the Lewis structure for the following atoms: hydrogen, oxygen, and fluorine. Pause the video if needed. Here are the answers. Notice that in the oxygen atom, there are 2 electron pairs and 2 unpaired electrons. Remember what unpaired electrons look like because you will need to know them for later. Next, we will draw the Lewis structure of molecules. To guide us, we will use the octet rule, which states that atoms want a full valence shell of electrons in order to have maximum stability. In hydrogen and helium, a full valence shell has 2 electrons, but for all other elements, a full valence shell consists of 8 electrons. Now, let's draw the Lewis structure of a methane molecule. Methane has a chemical formula of CH4. Start by drawing the least electronegative atom in the molecule, along with its valence electrons, in this case, carbon. Next, add the other atoms and their valence electrons around the least electronegative atom. You may realize that none of these atoms are following the octet rule. How can we fix this problem? With covalent bonds. Covalent bonds allow atoms to share unpaired electrons. Let's change our diagram of methane to include covalent bonds. In our methane molecule, this hydrogen only has 1 valence electron. In order to complete its valence shell, we can create a covalent bond between the carbon and hydrogen. This bond is drawn as a short line. Now, repeat the same process for each of the hydrogens. If you count the valence electrons, you will see that all the atoms have complete valence shells. Now, let's try a different example. Hydrochloric acid, or HCl, because that molecule consists of only 2 atoms, the order in which the atoms are drawn does not matter. We will start off by counting and drawing the valence electrons for each atom in the molecule. You should end up with something like this. Now, try and satisfy the octet rule using your knowledge of covalent bonds. Pause the video here if needed. Did you get something like this? In this structure, the hydrogen has 2 electrons and the chlorine has 8 electrons, satisfying the octet rule. On to our next atom. You may recognize our next example, water, which has a chemical formula of H2O. Try drawing the Lewis structure for this molecule on your own. Pause the video here if needed. Did you get something like this? In this structure, oxygen, which is less electronegative than hydrogen, is in the center of the molecule and bonded to the 2 hydrogens. The octet rule is also satisfied for all of the atoms. In special cases, single covalent bonds will not be enough to satisfy the octet rule. In the carbon dioxide molecule, single covalent bonds will result in incomplete valence shells. This can be remedied by creating extra bonds between carbon and each of the oxygens using unpaired electrons. These are called double bonds. In the nitrogen molecule, which has the formula N2, a slightly different situation is created, where even a double bond will not result in a full valence shell. In this case, a triple bond is required to create a full valence shell for both nitrogen atoms. However, there are some exceptions to the octet rule. The reasons are complicated, but elements from period 3 and lower can form an expanded octet. If a molecule contains an expanded octet, it has more than 8 electrons around the central atom. Keep in mind that only the central atom can have an expanded octet, not the surrounding atoms. One simple rule to follow in creating Lewis structures for molecules with expanded octets is to prioritize having complete valence shells in surrounding atoms. With that in mind, here are some examples. Phosphorus pentachloride, PF5, looks like this without any covalent bonds. Its Lewis structure looks like this. See how each of the valence electrons in the central phosphorus atom is bonded to a fluorine. This creates full valence shells in all the fluorines, but gives phosphorus an expanded octet. That's okay, because phosphorus is a period 3 element and has an expanded octet. Another example of a molecule that features an expanded octet is sulfur hexafluoride, SF6. Without bonding, it looks like this. Its loose structure, however, looks like this. Notice again how the surrounding fluorine atoms have full valence shells, while the sulfur in its center has an expanded octet. Now, try making the loose structure for sulfur tetrafluoride on your own. Here's a hint. There should be a lone pair. Pause the video here if needed. Did you get something like this? In the loose structure, all of the surrounding fluorines have complete valence shells, while the central sulfur atom has an expanded octet. After you understand how loose structures work, we can use them to determine the shape of molecules with valence shell electron repulsion theory, or VSEPR. VSEPR theory is a model that predicts the geometry of a molecule based on the premise that electron pairs repel each other. As such, we can use the loose structures which show electron pairs and bonds to predict molecular geometry. To do so, first find the sum of the bonds and lone pairs around the center atom. Based on that information, it is possible to determine the base shape of the molecule. Based on the number of bonds and lone pairs surrounding the atom, the molecular geometry will vary. If there are 2 or 3 atoms that align, with no lone pairs on the central atom, the bond angles will be 180 degrees, and the molecular geometry will be linear. Yep, as seen by the little gummy bear demonstration. Next, we have trigonoplanar. If the sum of bonds and lone pairs on the central atom is 3, the base shape is trigonoplanar. When there are 3 bonds and 0 lone pairs, the geometry is trigonoplanar and its bond angles are 120 degrees. When there are 2 bonds and 1 lone pair, it is bent trigonoplanar and its bond angles are less than 120 degrees. An example of this geometry is ozone. If the sum of bonds and lone pairs on the central atom is 4, the base shape is tetrahedral. When there are 3 bonds and 1 lone pair, the geometry is trigonopyramidal, and its bond angles are less than 109.5 degrees. An example of this geometry is PCl3. When there are 2 bonds and 2 lone pairs, the geometry is bent tetrahedral, and its bond angles are even smaller than 109.5. If the sum of bonds and lone pairs on the essential atom is 5, the base shape is trigonal bipyramidal. When there are 4 bonds and 1 lone pair, the geometry is seesaw, and its bond angles are less than 90 degrees and less than 120 degrees. An example of this geometry is SF4. When there are 3 bonds and 2 lone pairs, the geometry is T-shaped, and the bond angles are less than 90 degrees. An example of this geometry is ClF3. If the sum of bonds and lone pairs on the central atom is 6, the base shape is octahedral. When there are 5 bonds and 1 lone pair, the geometry is square pyramidal, and its bond angles are less than 90 degrees. An example of this geometry is ClF5. When there are 4 bonds and 2 lone pairs, the geometry is square planar, and its bond angles are 90 degrees. An example of this geometry is xenon F4. Before we conclude our lesson, let's learn about equatorial and axial positions. Imagine a globe. The axis of the globe around which it revolves passes through the Earth vertically. The crater circles the Earth on the horizontal plane. Similar ideas apply to the octahedral and trigonal bipyramidal based geometries. Atoms above and below the central atom are considered to be in axial positions, while atoms circling the atoms are considered to be in equatorial positions. When drawing the Lewis dot structures for molecules, we draw the axial position atoms first in most cases. However, for octahedral molecules and all its variations, equatorial position atoms come first. That's all for today's lesson on Lewis dot structures. Hit the like and subscribe button below, and for more informative chemistry lessons, email jk2002thebest@gmail.com and check out our other videos. Thank you.